Thank you very much for the introduction, and it's been a great morning. I look forward to this afternoon and talking a little bit about things more terrestrial at this point versus some of Anna Marie and Miguel's presentations, which were fantastic, by the way. And congratulations on all the student projects, too. I mean, those are some very, very interesting stuff that you guys are doing. So I had some fun looking at some of the posters and interacting with you. So before I jump into my stuff, I'm going to talk predominantly today about additive manufacturing. And really the thrust of what I'm going to cover today is what we predominantly look at GE Aviation / now GE Additive, whom I represent, which is in the additive metals arena. So I'm going to talk about laser-based powder bed systems and the electron beam powder bed systems. So the genesis of me becoming involved with GE began in 1994 when my brother and a mutual friend of ours and myself started a company called Morris Technologies in Cincinnati, Ohio. We got involved in the stereolithography technology, so that technology was born in Valencia, California in the mid-'80s, created by a gentleman named Chuck Hall, who took a combination of lasers and photopolymers and CAD systems, and you combine all that, and he made a machine and a company he created called 3D Systems. And so that was where we started. We started with some very expensive silicon graphic workstations, a couple of very expensive seats of SDRC Ideas at the time, and a used SLA 250 machine, which also was very expensive. So nothing was cheap about the startup that we had. But we organically grew over time, and we're very fortunate to just keep reinvesting in the business. We grew and added more capability on the additive front. But for us, what really changed the game is in 2003, we introduced a technology to North America called direct metal laser sintering. And that was produced by a company out of Munich, Germany called EOS. And that was the first powder bed laser-based system that was introduced into this region of the world. That really became our niche. That's what we ended up becoming very well known for. So we started with a CO2 laser. We graduated 2 years later up into a fiber optic laser. And with the fiber optic laser, it opened up an entirely new world of alloys that we could functionally use versus the alloys that we were able to use with the CO2 laser. So shortcut of it is we just kept reinvesting in that particular niche of our business. We didn't make the technology. We didn't make the machines. We didn't invent the machines. But we really were very instrumental in trying to take and use the technology and make the applications, or at least suggest to companies like GE and other companies how they could leverage this technology and make functional parts. So a lot of the presentations, whether it's Blue Origin, NASA, anybody else that's making parts, additive is going to play, already does play, but will play a larger and larger role in how the parts that they make are going to achieve their missions. And the missions could be in design, it could be in weight reduction, it can be in a whole ton of stuff. And so I'm going to walk through some of the stuff today about what GE Aviation has done and how we've used the technology on air-breathing engines to really fundamentally change the way that a lot of our engineers and designers are thinking today. And then I'll transition into a little bit more about what GE Additive does. So first and foremost, I don't want to assume that everybody knows exactly what additive is. I use that, and sometimes I go flying 1,000 miles an hour and I need to stop and just explain some of the basics. So real quickly, additive is a means by which we are creating a three-dimensional part from a 3D CAD file, and we do it layer by layer. There are many modalities, a lot of materials. So there's polymers, there's metals, there's ceramics, there's food, chocolates, cheese, you name it, etc. I mean, additive can be used to create objects layer by layer from that 3D CAD file. So we slice a 3D CAD file into very thin layers. In the case of metals, it's typically about 1/3 the thickness of a human hair at a minimum. So we're creating very tiny layers, and we stack those one on top of another. Now we do that by, in the case of what we use in powder bed systems, we're in essence micro welding one layer on top of another. And you come out the other end with a fully functional, fully dense, mechanically very robust component. I'm going to give a quick little video that gives the basics of the powder bed system. In this case, it's sort of showing what the concept laser-based powder bed system and how it operates. So I'll do this quick video and then we'll continue.
What is additive manufacturing? Additive manufacturing, also known as 3D printing, is a process that creates a physical object from a digital design. An engineer designs the object using computer-aided design, or CAD software. The 3D design file is then sliced into thin layers and uploaded to an additive manufacturing machine. The manufacturing process begins once an extremely thin layer of metal powder is spread across the platform. A heat source, such as laser or electron beam, then melts the first layer of the 3D design. The platform is lowered, and another layer of metal powder is spread across the platform. The layering and melting process is then repeated until the part is complete. The metallic powder is removed, and a physical object is revealed. Additive manufacturing allows you to produce parts that are lighter, stronger, and more durable than traditionally made parts. Build times are faster. Engineers can add precise features and complex geometries without increasing cost. In fact, additive manufacturing is revolutionizing the way we work.
Okay, so one of the things that there's a ton of little details and nuances, but one of the great things about additive is that the powder we don't use, we can recycle. So we re-sieve, we can reload that, we can put it into the next build. So you can do that both for the electron beam and for the laser-based powder bed system. So a relatively green process on that side of the equation. Okay, so on this chart, I think, as I just explained, as the video said, you can get a lot of complexity in what you design and then go create. And this is what's disrupting people's thinking. So if you've been designing traditionally for 20 years, this sometimes takes a little bit of time to get over that hump to realize, oh, I have all this design freedom, and how do I leverage and use that design freedom? So one of the not terribly obvious things sometimes is that when you add complexity in the traditional world of subtractive manufacturing, castings, forgings, machining, fabrications, brazing, welding, obviously what happens is what you can see on that red line, is that the more complex you make that shape historically, the more costly that part is. Also, the lead times go out because it's just going to take a lot more time and cost to make it. What additive ends up doing is the complexity, and people use this term, I don't like it a whole lot, but they say complexity is free in additive. And I'm not sure I say free, but it certainly is the case that if you have a highly complex part, what's driving cost is typically the height of the part, the amount of volume that the laser or electron beam has to consolidate, those type of factors. So you can get a very, very complex part, and the price doesn't correspondingly go up the more complex it gets. So what that means is the yellow section here, the shaded area over to the right, is a place where additive does just a phenomenal job. So you get all this complexity, you're not increasing your cost, and frankly, many times you're decreasing the lead time. Another element that we're trying to do at GE Additive right now is we're trying to resource the companies we acquired, I'll get into in a minute, and we're trying to move that bar to the left, so a larger shaded area, meaning the throughput of the machines is faster, the size of the parts we can produce will be larger, et cetera, et cetera. So speaking of time, when you go through the design cycle time, for anybody who is involved in designing and producing components, typically you will make a design, and that takes a certain period of time. Then you have to go out and have those components created, and again, traditional manufacturing methodologies, that can take a fair amount of time. Take a casting. If you have a casting that's an investment casting, you have to have the tooling created, then you have to produce the wax patterns and get the foundry to then pour the part. You get the part, maybe it's accurate, maybe it needs to be tweaked. Your lead time goes flying out. What we found is that additive allows us to squeeze that time down and get more iterations out of the designs. So we get a better design, we do it much faster. So for all the schedules that typically head to the right and the costs that continue to go up, additive allows us to pull a lot of those lead times back to the left and reduce the cost curve. That's pretty significant, and I'll show you a few examples where that's actually been the case. So when companies start to engage in additive, one of the things that you notice is that there's kind of phases that people using the technology get involved in. And one of the first phases is, hey, I'm going to use this just to replace an existing part. So it's an apples to apples, and that's really the wrong way to think about additive. Then you start to think about it from a business standpoint of maybe I can use this in the sense of deflation. So I'll make a part in additive, I'll go to my existing supply chain, and I'll say, hey, look, I made this part in additive, it's less cost than what your cost is. and I'm looking for you to bring your costs down. So that obviously is kind of used as a hammer on the supply chain. Then that thinking gets into the third phase, which is where you stop thinking on part level thinking, and you start to go into system level thinking. So now instead of my thinking I have this part, I start to combine different components. So on a gas turbine engine, instead of my thinking I just have one component I'm trying to see if additive will be good with, I start to combine multiple pieces to make it a cost-effective solution. And I'll have some examples of that. And then finally, you really get into a new cost entitlement phase. And I would argue that GE Aviation in particular is really starting to enter into the phase 4 at this point. Most companies are probably, if they're still relatively new with additive, are in the phase 1 and phase 2. Just a business explanation, I think, more than anything else. All right, so some of you may have heard this story before about the fuel nozzle, and it's a great story. This is one where we, at GE Aviation, we did not own the IP, we did not make fuel nozzles, but GE made the decision in order to capture a lot of the aftermarket that they would get involved in making the fuel nozzle and designing it. It's where my company, back before GE acquired us back in 2012, we got involved with GE very early on. By the way, we were located right in the same backyard of GE Aviation in Cincinnati, so that made for an easy way to get involved with them. But probably about 2002, we started to get involved in this project. And in essence, what they did is they leveraged this technology in order to take a leap over the intellectual property that had been designed around traditional manufacturing of the incumbent fuel nozzle. In the process, what they were able to do is take what the traditionally manufactured component fuel nozzle was of 20 different parts, combine that down into growing just one part. Now, what's interesting is if you look here, this is really the business end of the fuel nozzle. The rest of this is actually traditionally manufactured today, but this, what we would call the tip, is this complex area right here. And it's hard to see in the sliced X-ray image, but there are snaking passages through there, tolerances held within a couple thousandths. You've got the fuel acting as a heat exchanger, in essence, as it swirls before it gets put into the combustion chamber. So the benefit here is that we went from, again, 20 different parts down to one, and we get 5 times the durability out of traditional manufacturing. And we got that because we could basically prototype or do the analysis, and we could find out very quickly where the stresses were. So in this particular case, this fuel nozzle goes onto our LEAP engine, which is the replacement engine to the CFM56. So of the 12 or 13 or 14,000 LEAP engines that have been sold, there's roughly about 18 or 19 of these fuel nozzles on every engine. So eventually we'll ramp up to about 40,000 parts that we have to make per year. So we're higher volume, very demanding atmosphere where you're in the combustion chamber and a very complex little part. And we get the 5 times durability again because we can design out stresses where they occur, which is huge. Now, when you think about that supply chain that was involved in making those 20 different components, they were machined, they were cast, they were brazed, they were welded, they were assembled together. Think of the logistics. Think of all the trucking. Think of the multiple engineers that had to get involved to make each of those components, the different companies that probably had to get involved. Now we print it as one component, and I like to think of that machine that you see up there as kind of a mini foundry because we put metal powder in, and we're consolidating layer by layer, and out the other end comes a completed part, more or less near net shaped part. Here are some of the benefits that we get out of the technology. So you can see we have a tremendous inventory reduction. I don't have 20 different components that I have to scale up for. I have metal powder becomes my inventory. My life cycle costs come down, my manufacturing costs certainly have come down, and we actually got a weight reduction on the part as well. Weight reduction translates clearly to better fuel savings, et cetera. So we really have a lot of benefits by having thought about additive, and I would say at an advanced level, but not the level that we ultimately got to. All right, so here's a couple examples. When we had the fuel nozzle success, about 2.5 years ago, a small team of engineers within GE Aviation, about 5 guys, went off and they were given a mission to create, take one of our smaller engines, a CT7, which is a turboprop helicopter engine. And we took that engine architecture and we said to that team, all right, guys, forget everything you knew or how you would design it traditionally, and just try to design as many components as you could or as you can additively. And that was really a turning point for us within GE. aviation, as well as kind of the seeds of how GE Additive got created. Out the other end, and I'll show you where some of these ended up landing, but out of the other end of this came a couple of cool parts. So the integral C-sump on the upper left, I show that more not because of massive part consolidation, but because that's a complex geometry. It's got the 5,000th gap I'm pointing to that goes throughout that part. So we had a lot of complexity we were able to bring into there. The combustion liner is a huge story. Usually those combustion liners are created and you have to laser drill thousands of little holes. Those holes are there to cool the combustion liner because it sits in the combustion chamber. What we ended up doing is we were able to additively produce that entire thing with very specifically shaped cooling holes. And the end result is we were able to get about a 400 degrees Fahrenheit drop in temperature. So 400 degrees Fahrenheit cooler on that particular component. For those who are involved at all in that kind of a field, you would know that you'd sell your kids for 50 degrees or something, maybe 25 degrees. It depends on your kid. But 400 is huge. Okay, and on a LEAP style engine, it's probably, this is a smaller, so on a LEAP style engine, it's probably about 125, 150 degree cooler temperature. Very big deal. Now the mid-frame superassembly is a really neat story. On the left is the traditionally designed and produced mid-frame superassembly. That consists of 300 different components. On the right is a single part that's grown. So you're going from 300 discrete different components that come together to make that superassembly, and now we've redesigned it with all the additive capabilities down to one part. Just a tremendous cost savings on the supply chain, on the performance, et cetera. So really a huge story. This one, these different components not only were the precursor to our chairman and to our president and CEO of aviation as well, getting excited about additive and how disruptive it was, and basically leading to our getting more vertically integrated in the technology. It also led to some design elements that made their way onto the advanced turboprop engine. So this is our advanced turboprop. It's a ATP for short, and it's an engine that's going to be slated initially for the Denali, Textron's Denali airplane. And what you'll see, and you'll read it here, is on the lower right is probably the most significant number, which is 855 different traditionally manufactured components were able to be consolidated down to 12. So we took a lot of those lessons of the 300 to 1 or the 20 to 1, and we've applied that to this engine. We see a lower fuel burn, we see weight reduction, and most importantly, on this particular engine, when the foundry called and talked to our leadership about, hey guys, we know you're pretty far along on the design, you guys have not sent us the request for quote on the structural castings. And it was a pretty good day for our leadership to be able to tell that particular supplier, there are no structural castings. We're going to be incorporating those and growing those. We're going to additively produce it. So a really significant leap forward. On the LEAP engine, the fuel nozzle is one of thousands of components. On this engine, additive makes up 35% of what that engine is going to be. So 35% of that engine is going to be additively produced. That's what those 12 parts represent. So GE Additive is not only involved in gas turbine stuff. I know this isn't medical oriented as a group, but we, as an example, the additive can be used across many different industries. So if you're involved in medical, if you're involved in dental, if you're involved in the oil and gas industry, you're clearly able to leverage the technology in a variety of ways. In this particular case, we can make a trabecular-like structure, so an acetabular cup for any kind of a hip implant. We do sell machines where companies, medical companies around the world, are producing these in volume. They can do them for bespoke components, or they can do them in mass, one size, mass volume. It's more beneficial to go with additive, and these are titanium parts up here, because you can get all that complex structure on the exterior where the bone ingrowth wants to occur, and on the interior you're just growing it solid. So you can create this highly complex geometry and do it in a more effective way. So that really begs the question, when you start thinking about the supply chain, when you start thinking about, well, where does additive go and how do I think about additive as I go forward? Am I going to go from what used to be a traditional casting and fabricating and machining type of world into a world where you have banks of these machines that are producing components? And look, the short answer is, in our lifetimes and our kids' lifetimes, and maybe for as long as we can see out, traditional manufacturing technologies are going to be relevant. They're going to be the way that many parts and components get made. I do think, though, that additive will have an increasing role as we go forward. And so some components become very good candidates. Some products become very good candidates to redesign and rethink about it, and then actually probably see facilities where you have multiple little micro foundries, if you will, producing components. So why do we think that? If you look at total global manufacturing output, now exclude the construction market, you're probably talking somewhere around $17 trillion, okay? So $17 trillion is the pool of opportunity. Now clearly there are going to be components that are huge and big and not good candidates for additive. So we're not going to try to argue that additive is got this entire universe of $17 trillion that we can go explore. But if you look at where a lot of companies are starting to consider of their products, additive ranks up there as one of the elements, one of the technologies that companies are looking at. So of $17 trillion, how much of that could be additive? Well, today it's about 0.03%. That's roughly what the industry makes up today of the total global manufacturing output. We think it's not such a huge stretch to believe that additive might make up 0.5%. If it made up 0.5%, you're up in that $80 billion type of range, $80, $90 billion. So it could be a pretty significant amount. And that's where really we're looking. Polymers is the king of the hill, if you will, in number of installed machines and how much polymers are used. Metals is coming along like a freight train. It's just, you hear it all the time. Metal additive is something that's growing by leaps and bounds. And if you saw the curve of machines that have been sold into the market, they are going crazy. So I don't think it's really a stretch to suggest that 0.5% will happen. It's when. Is it 10 years or is it 20 years? But the market potential is huge.
In every generation, there's a moment where everything changes. A breakthrough that ushers in a new way of doing things and ensures the world will never be the same again. This is one of those moments. Introducing GE Additive, a new business that represents GE's passion for the industry and its tremendous potential. Its capacity to make complex parts that were once impossible to produce, to speed up the manufacturing process, and open up a whole new world of design possibilities. At GE Additive, we're leveraging digital industrial capabilities and new technologies to accelerate innovations across industries. From aerospace, power, and automotive, to medical, architectural, and consumer applications. And as a leading user of additive parts, we're committed to delivering world-class machines, materials, and services for customers around the globe. And once again, expanding the boundaries of what's possible.
Okay, so one of the beautiful things about GE is that we have multiple different businesses. We have our aviation, our healthcare, our oil and gas, our power, transportation, energy, et cetera. So we have a variety of vertical businesses that fall under the umbrella of GE Corporation. What that means is we have a tremendous number of proof points that we can apply in any kind of a new technology. So we get involved in a lot of technology, ceramic matrix composites, additive, et cetera. And with additive, what we have seen is that aviation has taken the lead. They clearly have been the ones that have leveraged the technology the deepest and the fullest way so far. That makes sense. Our engines and GE Aviation are smaller. The components that make it up are very complex geometries with high alloys, and so the environment fits very well. But all of our businesses actually are starting to leverage this technology in a pretty major way. So what we see from GE's own world of products is why I think you feel this tidal wave of applications that are coming. So the rest of the world, there are many companies still that are using it and successfully applying it in their businesses. Some you don't hear about, some you do. But there are a lot of industries that are starting to come into play that are going to be leveraging this technology much more so in the future. So think automotive. You don't normally think automotive, but automotive has low volume as well as they have super high volume. And the cost points are coming down to a reasonable area where they're starting to think about, geez, not only can I use it for the experimental cars, I can take it up into the hundreds of thousands, both polymers, metals, and other. So we see the proof points. We see this industry is just growing by leaps and bounds. And again, another reason why we believe the opportunities are tremendous. So GE Additive is a separate entity under the umbrella of aviation today. In a couple of years, it'll probably be its own vertical within the GE Corporation. We sell machines, we sell materials, and we sell engineering consulting services, not in design, but engineering consulting to try to accelerate that time it takes to learn about the technology and to learn and have those epiphanies of how disruptive it can be for a particular product or a particular customer's business. We have a very large footprint globally already, and we're going to continue to build on this. So within Cincinnati, we have what we call our Additive Technology Center. It's about 150,000 square foot facility. And then we have multiple other facilities through our global research centers around the world. Our Auburn, Alabama facility, which is standing up building the fuel tips today. They have about 40 machines that are lined up, making those just that one single part for that one single program. We'll probably see that increase to about 60 or so in the not terribly distant future. Our advanced turboprop components will most likely be produced in Europe. And of course, the two companies that we ended up buying, one's in Lichtenfels, that's the Concept Laser, and in Mölndal, Sweden is Arcam. Those are the two companies we ended up acquiring last year. So late last year, we took a controlling interest in Concept Laser and a majority interest in Arcam, both powder bed machines. The Concept Laser is a laser-based and Arcam's electron beam-based. Won't spend any time right now going over the nuances, but both of them produce very nice detailed components in a variety of different materials. So we work in cobalt chromium, we work in titanium, aluminum, nickel-based alloys like Inco 718, 625, a whole variety, a whole ton of different materials, stainless, etc. And that's what a lot of the machines look like. Now, typically, the price point on these machines can have a pretty good range. So from the smaller M Lab you see on Concept Laser, that's roughly a $200,000 to $250,000 machine, up to the large machine, that's the X line, where you actually can see in front of the machine some little stairs that you have to walk up to look in the machine. So it's a big machine. It's probably about the size of this stage here. So that machine's about a $2 million machine. So you have a pretty good range there, and then on the Arcam, they're about $1 million to $1.5 million, depending on what options are required. And by the way, the A2X is a machine that we have multiples of those at our Avio Aero facility in Cameri, Italy. Those are producing an intermetallic material called thialuminide, and that's for our low-pressure turbine blades that we have going on to the GE 9X. So our business is looking to be about a $10 billion business in 10 years. So back to my $80 or so billion market potential in 10 years. I think it's very plausible that we could get to be a $10 billion business, and we're pretty focused on it. That means we would have to have roughly around 10,000 machines in service if we get to that point. Again, that's one of the reasons as we go out to democratize this technology, as we start to see this tidal wave, we think that's probably, again, pretty plausible. If you start to look at the curve of how many machines are getting sold and the backlog every year, it's growing by leaps and bounds. So we believe that with our engineering consultancy, machines, materials, that we should be able to achieve that 10 billion. And we want to be an influencer in the industry, at the same time recognizing there's a lot of great companies with great technology. We're very fortunate to compete against some other world-class companies out there. And as you'll hear and as we go forward, there are a lot of other companies getting more interested in different modalities and metals and polymers, et cetera. So I'm going to leave the presentation with one last item, which is a video. This is actually out of our Avio facility in Cameri that I just mentioned. And what you'll see are both the laser-based technologies in operation. You'll also see the electron beam technologies in operation. Now, in the laser-based business, you can get machines that have multiple lasers, up to, I think today, there's roughly machines with 4 lasers on them that can work at the same time. There are many of them out there that have dual lasers that are scanning at the same time. In these videos, everything is just a single power beam, okay? So you have a beam coming down, and it's roughly 10 thousandths of an inch diameter. Where you see it looks like a line, it's just moving very fast. Where you see multiple spots of light, especially on the electron beam, it's one source, it's just jumping around so quick that your eye can't keep up with it. Every video you see of the machines in operation are real time, so nothing's been sped up. Okay, so let me play this and then maybe we'll have a few minutes for questions. Okay, so thank you very much for your time. I appreciate it.